Thanks for coming to my talk, and thank you to the organizers for organizing this wonderful workshop and giving me the opportunity to talk. I will be talking about work in progress with Ziwen, who is here, and Peter Kravchuk from King's College. We've been working on it for 3 years, but now we really should finish it because Ziwen is applying for postdocs. And so hopefully it will come out soon, unless you make her a very quick offer, and then we can continue to procrastinate and add more to our paper. So if you want to scoop us, that's the way to go. Already some of these people, including my co-author, scooped small parts of our paper. But we still have a lot more that I will cover. So I'm not going to write many archive numbers on the blackboard today, but I did write this one, which is my first paper on the archive. And the fourth equation in that paper is the following. Describes a Wilson line in n equals 4 super Yang-Mills. And in that paper, among other things, it's a long paper with David Gross and Hiroshi Oguri. Among other things, I think the main thing we wanted to understand is, what does this coupling mean? And we understood it as related to the embedding in ADS-CFT, and we understood it as relating to the embedding of the string into the S5 part of ADS5 cross S5. And then you think, okay, that's well understood and we can move on. But turns out that 26 years later, I'm still trying to understand what this means, and I will tell you about it in my talk. So if you think you're a PhD student and you can work on whatever project you want and then move on to do something else, that's not the case. It sticks to you. But for the purpose of the talk, I will tell you some things about Wilson loops, but that is actually not so important. And I don't really need to worry about things like, I don't want to really worry about trace and path ordering. They're sometimes important. So we can take as our canonical example as the line defect in the Owen model, say in 4 minus epsilon dimensions. But we really don't need to be very specific. So I will consider an operator which takes the form integral of ui phi p tau. P can be 1, the dimension of the defect. And there's going to be some, say, coupling such that this may be fixed by RG equations. And then my u will have norm 1. So there is such a line defect in the Owen model, p equals 1. And both of those things I can take to functions of tau. Phi, of course, is a field, so it depends on tau. So I'm going to have such an insertion into my Lagrangian, which will flow then to a conformal defect, and I will work with that. If you don't have a Lagrangian, a lot of what I say also applies, but let's try to keep things relatively concrete. Now, as we know, as has been said a million times in this workshop, when we have a conformal defect, we break SO2 plus 1, comma 1. And let me assume some global symmetry G. is broken to, so p plus 1, comma 1 times O v minus p times h. If you want to be concrete, you can take G to be On. If you like n equals 4 super n mils, you can take n to be 6. And let me take H to be On minus 1, but I will talk a little bit also about more general cases. And this is for the symmetric defect. So this is true for constant u of tau, and I really should write here phi of x of tau for constant u and constant x of tau. If they are not constant, I can break it much more. Or I can say that locally this is the breaking of the symmetry that I have. But this is what I want to describe, and this is what we have. So this is the defect CFT that we want to work with, or what this half of what this program is about. But what I want to understand is actually a general Wilson loop, or a general defect with an arbitrary shape and arbitrary profile among this scalar directions or global symmetry breaking. So how do I go from this symmetric CFT point of view that I have back to this? Now you can say, okay, I don't really need this CFT. So in my old paper, we didn't use defect CFT techniques because that thing didn't exist yet. So we were studying this directly with an arbitrary smooth path and so on, but you can get only so far by studying arbitrary shape. And it's much easier if you fixate on the very simple shape. And then you're going to tell me, as I've told many people in many talks, that we can view this U as close to the identity. So I will write it as a delta I n plus wi, and I will assume that w is small. And then I have a small deformation of the uniform embedding. Likewise, I can take x mu to be equal to a constant, sorry, to be planar. So it's going to be tau, essentially plus a small deformation in the normal direction. VR, I'm messing here up the indices, but forgive me for that. So this is the parallel direction. These will be the normal directions. You can put proper projectors to make this work. And in the internal symmetry, UI, I can think of WI as belonging to H perp inside the algebra G. So it's the part orthogonal to the algebra of H. So that is what takes me away from the fixed point. So I have all these directions, which in the case of, so of course, On mod On minus 1 is equal to Sn minus 1. And in this case, H perp is going to be a Rn minus 1. I have n minus 1 directions where I can deform my straight uniform defect. Likewise, here, I'm going to have the generators PR, KR, and the rotations MAR, which are broken. And with them, I can deform the shape. And a very naive kind of thing that I would write is that my defect with an arbitrary x of tau and u of tau, I would want to write it as e to the integral v of r PR plus wi what is it, hi, or the group generators, yeah, d tau acting on w, which is a straight line. So delta in and whatever u naught. So if you had a point particle and you wanted to translate it, you would act with this. And now we have a defect, and we want to translate it according to an arbitrary profile. These are functions of tau. These are functions of tau. I want to give it an arbitrary shape. This expression doesn't make sense as it stands. And the purpose of my talk is to explain how to deal with this. You look confused, Matt. Okay, so of course we can start by just expanding this. So we have this is equal to 1 plus we have P acting on the defect. That is what we call the displacement operator, VR dr, plus Wi Pi, that is the tilt operator. So that's what we get from the broken generators acting on our defect. And they are integrated. And then we have the double integral of Vd plus Wt squared, higher order terms. And the reason this expression doesn't make sense is that you have here all these operators that can come on top of each other. If you really want to understand a finite deformation, you need to worry about what is d squared at one point, or what happens when this p acts again on this d. As long as all of these guys are separated, life is easy. Once they start hitting each other, things get complicated, and this is why this expression doesn't make sense or needs this talk to explain it. Any questions so far? So let me illustrate this issue in a very simple setting. So I want to find an arbitrary profile using these infinitesimal deformations of my symmetric defect. So in particular, I have this Sn minus 1. And now I want my defect, so it starts off living here along the entire line or surface. It's fixed at that point. Now I want it to travel a little bit. So I want to use these coordinates that I call W to describe a position on the sphere. So that is very easy. I can take, for example, W at delta IN, the North Pole, plus W of tau. I can take this to be e to the minus h star integral d tau 1 over square root 1 plus W of tau squared by n plus W I phi I. So now I have these vectors Wi that tell me in which direction away from the North Pole I'm going and how far away from the North Pole I'm going. And I introduce this factor to keep the norm 1. So I still satisfy the condition that this is at the fixed point locally. So everything is nice. And if you think of what these W's parameterize, if I take W to infinity, then I have it coupling only to, this is infinity, this is infinity. So this term goes away. It means that I'm sitting here at the equator. So I can say that this coordinate patch covers half of my sphere. And you really can think of it as related to the metric ds squared is equal to some constant dwi over 1 plus w squared minus wi dwi squared over 1 plus w squared. So this is the natural metric that you would associate with this structure. This CT is the radius square of my sphere, and it is natural to associate it to the two-point function of 2 tilts, Ti of tau, Tj of tau. They have some Lotikov metric on them, so locally it's going to be some constant Ct delta Ij over, sorry, this is tau 1, tau 2, over tau 1, 2 to the 2p. I didn't mention the tilts have protected dimension p, or 1 for line defects. And this is a choice of a metric that covers half of my sphere, but let's say that's good enough for now. And maybe that's how I define what this deformation does, what W is. But of course, this is not a unique choice. I can choose another metric for my sphere. So for example, stereographic coordinates with ds squared is equal to Ct dwi dwi over 1 plus 1/4 w squared squared. This you can relate it to e to the minus h star integral d tau. Sorry, there should be a, oh no, that's okay. 1 minus a 1/4 w squared 1 plus 1/4 w squared phi n plus wi phi I over 1 plus 1/4 w squared. And that is another choice of a metric on the sphere, and another choice of how to turn on these w's. So if I set here w to 0, this goes away. This is 1. I go back to the previous one, the same as here. To linear order in W, this is just 1. I have u phi plus something small times phi I. I get the exact same thing here. So both of these metrics, both of these parameterizations of my deformations of the defect agree at the constant level and at the linear level, but they don't agree at quadratic level. Now, why is this stupid geometry relevant for us? The reason is that we define the tilts as a linear deformation of our defect. So all we have is the information at the linear order, and we don't know. In any CFT calculation, we're not going to know if we're in this with this metric or with this metric. So we need a formalism that is agnostic to that. And we need to see how does the CFT tell us which case we're in, and what do we do? How do we work with an arbitrary, without knowing what our metric is on our space? I should add both of those are Riemann normal. So that can't help you. Riemann normal also only tells you how things behave at a linear order. No, these two metrics are different. Everything is consistent, they're just different. Okay. So I had the word ward in my title hidden. So what we're actually going to be interested in is the nonlinearly realized broken symmetry. At quadratic order, it's pretty good. It's pretty okay. Yeah. It has some subtleties already at quadratic order. There are contact terms, but we sort of know, it's pretty well known what contact terms are at quadratic order, and therefore you can think that this is not that. But at higher orders, you get more contact terms that are less well understood. Does this answer your question? I didn't let you finish it. So there is the symmetry, which we'll say is SON or G. And I will take an element e to the lambda to be in G. So lambda is inside the algebra. And then the statement that I have an underlying global symmetry G to my theory is that if I take my defect with, instead of a U or W, I transform it with a Lie derivative e to the lambda of W, I will get a transformed defect, which should be equivalent. So the expectation value of this defect should be equal to the expectation value of W with these deformations. W, I can take it to be the small deformations W or U, that doesn't matter. But symmetry is such that sometimes you get an anomaly. So you need to allow for an anomaly which can depend on e to the lambda and W. And you can do the same thing for space-time translations and so on for the space-time symmetries. Here I only wrote the algebra and transformation for the internal symmetry. Yeah. Anomaly. So the word is because the naive symmetry transformation would say that the transformed object would have exactly the same properties as the original one, but you know that in a quantum theory that may be violated slightly, and the violation is related to the addition of possible local terms in the action, and these will change the answer by a numerical factor. And it's called a quantum anomaly. Did this answer your question? Okay. So I need to specify how L e to the lambda acts on W. And so I'm expanding in small lambda. So at linear order, I will just go back to myself. I'm going to get L, which is a function of lambda and W. And I'm going to get things at order lambda squared. And I'm not going to worry about them. So in that way, my title is misleading. I'm not rewarding by acting twice with lambda, but it will be rewarding. And I am considering things at arbitrary order in W, and that plays a similar role and actually gives me even more freedom. Just one distinction, lambda is a constant, and it's in the full group. W is a function along my defect, and it's in the perpendicular directions. It's in H perp. So it only sees the broken directions. Let's continue like this. And now I expand L of lambda and W in a power series in W. What is it? Sum 1 over n factorial ln lambda and W's. So it's a symmetric polynomial in the W's, or it's a general kind of thing that you can have in this power series. Now, the first term, L naught, has no W's in it. And I will assume that it's lambda perp, so it projects out the symmetry directions. I don't have to do that. I can have crazy things where I violate the symmetry. The symmetry already acts non-trivially before, but that is a bit of a crazy choice. And again, a bit more notation of lambda I EI. So EI is a basis of H perp. And now you can calculate these L's explicitly for the metrics. So say you give ChatGPT this metric and you ask it to give you the killing vectors for this metric, or you can find it in textbooks, or you can look up how to calculate killing vectors and do it. All these things will work. And for metric 1, what you find is that Li is equal to partial I plus Wi Wj partial j. And for metric 2, Li is equal to partial I minus W squared over 4 partial I plus 1/2 Wi Wj partial j. So as I promised you, these metrics differ at the quadratic order, and you can actually see it here on the Killing vectors. The Killing vectors are the same at linear order in W. They both vanish, sorry, at constant order in W. They both vanish at linear order in W because it's Riemann normal, and at quadratic order, they are different. So now we learned that Killing vectors are not an invariant of a geometry, but maybe we already knew that before. We do know that at quadratic order in the geometry, you can construct a covariant, which is the Riemann tensor. Riemann tensor. And that is the one quantity at quadratic order that you can get out of it. And I can read off, so in both of those cases, I will have that L0 is equal to essentially EI. That thing, L1 is equal to 0. And then L2 will be different. You just read off what it is from here. In the first case, it's 2Wi Wj Ej. In the second case, something slightly different. And in both cases, you find that L2 of lambda W minus L2 of lambda W, and I really should stick with regular L because curly L plays a different role for us. This gives us the same. It turns out that this is related to the Riemann tensor. And we found an invariant at this order. So this was from the geometry point of view. I just started with a metric. But this will have a meaning in terms of the CFT calculation. So in principle, every time you do a calculation in the CFT, you can act with the symmetries. You can evaluate correlation functions. You're going to have the analog of these quantities. L2 will be scheme dependent. It will not have a unique answer, but you can choose your scheme, do the calculation in that scheme, find an answer for L2. Then you will know, if you care, what is the metric at quadratic order, but I don't really care. What I do care is that I can find a combination that is scheme independent, that is coordinate independent. And then we find non-trivial identities, and that gives meaning to this relation at the bottom. Sorry? The curvature doesn't affect the anomaly. This curvature doesn't, but there are terms in L2 that can affect the anomaly. I will get there.
So in this sense, we separate the whole two arbitrary tensor like covariant Riemann tensor and matrix from the W coordinates, right?
So, okay.
It bounded
That's,
for-
so I'm not sure that I understood your question, but it reminded me of something important I have to say. Maybe it is related to your question. So I did here a horrible sin that I wrote two metrics with the same coordinates, both of them with W. So, but this is the sin that we are facing. We do not know what the metric is. So I have here some W, and I don't know if this is my metric or this is my metric. All I did was define things to linear order, and from then on we're blind. And we just get some quantities, and we hope to find things that are invariant under them. And, well, we do. And that have meaning. I don't know if this was your question. Okay. Okay.
Can you say again what is the ordering inside the
Yeah. So L is defined like this. So lambda is my global symmetry. W are my coordinates. L is an expansion in terms of it. So it still has one lambda and one W, but then it's just a function. And then it turns out that that combination where I change the order, so this is symmetrized, this is completely symmetrized. So you just take that thing, so you just take this function, sorry, this is lambda I. So that is why I have here a coordinate. So you can see how you get this for a function of any three variables. It has to be symmetric. So if you exchange the order of lambda and W, you're going to get two terms because of the symmetrization. One of them contracted and one of them not. Did this answer your question? I can write it in a bit in more detail. What? I mean, actually, for the second metric, you already have this form here that I need to write in like that, so it will come out, will be a bit more explicit that you have this symmetrization. Wi, Wj, Ej minus a half W squared Ei. Yeah, and then you put it in a symmetric way. You have to symmetrize here. Here it's automatically symmetric, and you get that, and you find answer.
Is this similar to the geometrical tensor?
That's right. So this R is a tensor. It's the Riemann tensor.
Yeah, but you know that in convex community they will use it. They will define the tensor simple power give a metric, and this simple power gives the curvature. So is this same thing?
The Riemann tensor is the Riemann tensor. For this, I have here a geometry.
Geometry tensor is also give a simple defined by the state. They will give a quantum state, and they can define the geometrical tensor. And then simple
What tensor?
Geometrical tensor. Do you know this tensor?
No, I don't.
Okay,
So, to be explicit, we're going to be looking at a Ti1 up to Ti1, Tik of tau k, and this will be equal to a function of tau1 up to tau k. But actually, this quantity is not a function. It's a distribution. There are going to be contact terms in it. So I will take this to be the functional part. So this is at separated points. And then I'm going to have delta tau1, 2 times a function of tau2 to tau k plus other ones plus delta tau1, 2 delta tau1, 3. So I'm going to look at all contact terms in this quantity. Normally, what we calculate is only the first one at separated points. But in order to make sense of anything I'm saying here, we need to worry about all of them. So this is well defined. You learned your quantum field theory. You can do a calculation. You're going to get an expression for it. This one will be related to L1. This one will be related to L2. This one will be related to L3, and so on. And these, as we saw, they depend on metric. And here, these depend on local terms. In the action. So it's what we will call scheme dependence in QFT. So you can take two approaches to dealing with this problem that I had at the beginning. One, you can choose a metric and make sure that everything you say is consistent on the two sides. Good luck with that. Or two, work in a scheme independent formulation. Then you find these identities, like I wrote for you before, of L2 minus L2. And then you can choose any scheme that you want, do that calculation in that scheme, and you're going to get a meaningful answer. In this way, you can also do it in principle. It's a little bit hard. I would say that these papers sort of, the papers that scooped this sort of did it this way. It's then a bit subtle to know whether what you did is actually scheme dependent or not. The quantities they found were really scheme independent, but it's not a priori obvious. And in this way, you really derive what is scheme dependent and what is scheme independent. So as far as the CFT is concerned, what we are looking for in L1, it's related to whether T appears in contact terms of the TT OPE. L2 is related T inside T times T contact terms. By the way, from group theory, you will see that in the case of the ON breaking to ON minus 1, this doesn't arise because just these are in the normal direction. The normal directions to ON minus 1 don't commute to another generator of ON minus 1. Sorry, commute to a generator of ON minus 1, not to another normal direction, but with other symmetry breakings, this can happen. And L3, and so on. So actually, the anomalies, you can also expand them in a power series, AN of A. So we're going to have A1 of lambda, A2 of lambda and W, A3, sorry, this is A0, this is A1, I should learn to count, W, So this is related to this is related to the identity contact term inside TT. No, that is because this is Riemann normal. But if you had so this is because it's a homogeneous space. So a homogeneous space is such that the commutator, so the commutator of H perp is inside H. So that's what happens in this case. More generally, it doesn't happen. I don't, maybe, no, I'm not sure. I don't think that it's, maybe, no, maybe it is. Sorry, I can't, I won't be able to answer it now. Yeah, it is the same L. So yeah, so if this is so there will be some linear term, I think. Yeah, I think you are right. But this relation is related to the question I got before about whether this makes sense at a quadratic order. This relation down here, and at a quadratic order, we can get an anomaly. So that is what we know, that t times t can have an anomaly in it, or displacement time displacement has an anomaly in it, and that is already some subtlety arriving at the quadratic order. And this is the identity inside t times t. Now, everywhere you can generalize it to not only have tilts and displacements. And all these correlation functions I wrote, I just had the tilts, but you could have other things, and then you would calculate things like an operator O inside the T O OPE. So you take, well, you can take one, or you can take two, all of them at the same point. There's going to be a contact term there that will bring you back O. So our formalism allows for this extra structure, but it sort of complicates things. These other papers, they looked at this. Essentially, what they do is this way of doing it. So essentially, they calculate things like order L1, but with an extra operator on top. So I talked for a long time about formalism. Let me show you some results that we get out of this. It will be a bit schematic. The Wen in her talk will actually also look at that case with extra operators. So that is based on a paper with Jake here, where that operator is not on the defect. So that is a correlation functions of defect operators and bulk operators plus extra tilts, and they have relations that they satisfy, and that's what she will explain in her talk on Friday, and she will give a lot more detail than my schematic talk. In this thing. Yeah. So everything here has indices. Yeah.
But then this, what appears in the delta and first order anomaly, do they have anything to do with things that we already know, like the three-point function of the tensor has a delta function that goes like
Yeah. It's exactly the same kind of thing.
Oh, okay.
So the right-hand side should have all possible tensor structures. And if you know how anomalies appear in correlation functions of energy momentum tensors, here we're looking for similar kind of things, how things appear in correlation functions of displacements and tilts. So for example, in your paper, you had a 3-point function of tilts, and actually, in that case, it would be epsilon ijk of SU2 inside TI, TJ, TK, OPE. There is a contact term that you didn't calculate, you didn't have to, but secretly there is a contact term that needs to make things consistent. Yeah, I didn't write there the tensor structures. So let's start with n equals 0. So I'm just acting with one global symmetry on my defect. So I can write it as the integral lambda I, expectation value of Ti tau dp tau, that is equal to 0. The anomaly at this stage is 0, so that is that's at least my assumption. So this is a very stupid statement, you will tell me, because the 1-point function of a tilt or any operator in a CFT that is not the identity is 0. But actually, I didn't tell you what this is. I can put here anything else. So it's true for any correlation functions as long as I don't have I'm not thinking about extra contact terms. But I'm allowed T to act on any of the other, to meet. As I integrate it, T can hit any of the other operators. I don't even need to assume conformal symmetry for this. This is always true. It's just a consequence of the global symmetry. Now, there was to show you some real application, there was a paper of Gimene Clau and Liendo that calculated 4-point functions, tilt 4-point functions in n equal 2 theories. So they generalized what was done in n equals 4 theories to n equal 2 theories in the case of the Wilson line and n equal 2 theories. And what they found is that t to the 4th was equal to t to the 4th in n equals 4 super in Mills times alpha plus beta and another function of I, J, K. M, the indices and the cross ratio Z. So it was an analysis in analytic bootstrap, and they found that at strong coupling and so on, you can get the same answer as n equals 4, which is obvious. Plus, there is another function that can show up. And now you do the integral like here. And you get the integral of the thing in n equals 4, which would better be equal to 0, because n equals 4 is a good theory and satisfies everything you want, plus beta integral of f. And this turns out, you calculate it, it's different from 0. So one simple integral that they did not know would tell you that beta is equal to 0. and tell you that the answer for n equals 2 theories is the same as for n equals 4 theories. At leading order at strong coupling. So these are theories that have a holographic-like behavior. A large n, you can expand in generalized free fields, essentially, and you reproduce that it's, if under that assumption, the answer is the same. There is no extra freedom. It is theories, so, okay. So you have to read their paper to get the exact regime where this calculation is valid, but it is essentially where you can do the analog of ADS calculation. And then this is analytic bootstrap, so you take all kinds of assumptions of what can appear in the OPE and so on, and then I don't know how, it's a bit of a black magic, and people did it to essentially reproduce the answers they knew from Witten diagrams in n equals 4, and then they justified it as actually natural in this kind of expansion near generalized free fields in ADS. And there is similar statements of Pozzi and Troncanelli for 3D n equal 4 theories that was generalized from ABJM. They again find another function. If you integrate over that function, you find a non-zero answer. So the answer is that the answer is the same in n equals 4 theories as it is in ABJM. Pozzi recently had a solo paper where he proved it using very, very complicated formalism and a lot of assumptions. And essentially in your paper, so this is 2D ADS 3, also you find a bunch of functions, and you can also restrict them to fewer functions by imposing this condition. Now, this is so far not rewarding enough, because this is just one application of the word identity. It's linear. This is linearly realized symmetries. To get the non-linearly realized symmetries, you need to go to larger n. So for how long should I go? Okay, easy. So for n equals 1, what we have is a, yeah.
Why n equals 0? It's because it comes from a different Lagrange, or you know the answer from the other.
So
you have your integrated constraint.
Yeah. So so n equals 4 satisfy the integrated constraint, and therefore the integral of this, the full n equals 4 answer, has to vanish. This is something extra that n equals 2 allowed, but it doesn't satisfy the constraint. Therefore, this is linear. So if this satisfies it and this doesn't satisfy it, then the coefficient here has to be 0. Of course, in all of these papers, they do not write their answer like this. They split it in some other way to make it look more interesting, but it really is the same. And of course, well, they didn't have this relation, so they don't know that the second part is 0. It's a bit of a downer, I guess. Everything is n equals 4 at the end. Yeah. It can.
Cannot be a bulk operator when you set anything. Because if you insert the bulk
So sorry, it's anything on the defect. So if there is a bulk operator, the symmetry can act on it separately, and you still have an identity, but there is something non-trivial on the right-hand side, and Ziwen will talk about it on Friday. But it's equally simple, just not zero.
You can use like this sort of thinking to say something non-trivial about Wilson and some theories that are not supersymmetric, or there will be
I didn't. So these people constructed this in supersymmetric theories. This statement doesn't require supersymmetry. The ON model is not supersymmetric. So if you do analytic bootstrap in a non-supersymmetric theory and constrain the form of the function, that would still be valid. This was just one example of how you can use this identity, but this identity is completely general just because these people went through the trouble of finding these functions. That I get something that I can do very easily. Just take this, put into Mathematica, press Shift Enter, you get an answer that is pi times something. That's it. All other cases you need to work harder. So for n equals 1, I need two tilts. I have integral beta 1, t1 of tau 1, ti of tau 1, tj of tau 2. This should be equal to 0, which you will tell me tells me nothing more than I already knew from here. But that is not quite right. So first of all, this two-point function I told you will be equal to ct delta ij tau 1 2 to the 2p. And because I'm dealing with the L1 case, this identity, unless I have here an anomaly, this identity should include also contact terms. In this case, the only contact terms that can arise are anomalies, and actually they do arise. In the contact term of two tilts or two displacements, they are integer dimension operators. So for p equals 2, this thing does not behave well at coincident points. And what you get is some log divergence times partial p delta p tau 1 2 as the contact term. And the coefficient of this is some anomaly coefficient. And this, in our formalism, this arises in this equation on the right-hand side of it. When you act, it's not quite here. You need to act with a conformal killing vector on this identity, and then you find this anomaly. So it's, strictly speaking, the anomaly that I will find is for a killing vector and in two of these W's. And it will capture this behavior, which has been well known, that it's the same CT up to a number that appears here. This So in the case of the, it's better known in the case of the displacement. So this is an anomaly that was found by Bianchi and Mineri and Myers and Smolkin in the context of Renyi entropies, but it's relevant here as well. And the same is true for tilts. They have a similar kind of anomaly. It's just less explored in the literature. So for n equals 2, we have the integral d tau 1 of t out of tau 1 tj tau 2 tk 3. And this is also equal to 0 or an anomaly. And now the 3-point function in a CFT is equal to some structure constant dijk over tau 1, 2, tau 1, 3, tau 2, 3, all that to the power p. But actually, this exact integral is what you would get if you tried to calculate the 2-point function of tj tau 2, tk at tau 3, to linear order in conformal perturbation theory. So if I start with a trivial defect and calculate this, I deform my defect with keys that are marginal operators, I will get this thing at linear order. And this thing better be finite. But the integral of this is logarithmically divergent. Just because you have here an integral, just d tau 1 to the p, find that it's logarithmically divergent. So the conclusion is that dijk is equal to 0. This is standard statement in CFT. Of course, we want to understand it also at coincident points. At coincident points, it can be different from 0. Then if there is a contribution, if there is a delta function contribution, you're just going to get an extra number on the right-hand side. That's completely legal. It means that your metric on the defect conformal manifold changes a bit as you move at linear order, which means that you chose a different metric that has a Christoffel symbol. So the contact terms that you add to this, so you have this plus contact terms. These contact terms are related to Christoffel symbols if you choose to work not in Riemann normal coordinates. There is one exception to this, and that is for line defects oriented lines. In that case, you can have a 3-point function equal to fijk over tau 1, 2, tau 2, 3, tau 3, 1. Now without absolute values. The integral of this is 0, so it doesn't mess up with a conformal perturbation theory. So this quantity is allowed, and it arises in 2D CFTs or in their holographic dual, like in the paper on ADS 3. So you have a non-zero quantity, but, and I will not show it here, it does lead to an anomaly. So in order to have this term, you cannot have the On broken to On minus 1, because you need this kind of structure constants Fijk. So the simplest case is when you break SU2 completely. And then you have 3 tilts that will that can have this kind of property. You can see, you can get it in WZW models or in this holographic model of Ignacio. And there is an anomaly A2 of lambda in W and W is different from 0, and it actually tells you that W, the defect, is not a function, is some kind of line bundle. So there is some topological classification. It belongs to a second homotopy group of something. And there is some complicated global anomaly that is captured by this and is a consequence of this term. But I don't have time to elaborate on this. As I said, Ziwen is going to give you more details than you will ever want on any of these calculations, or similar ones, or the bulk defect case. So let me conclude with the n equals 3 example. So now we're going to have integral dp tau 1 ti of tau 1 tj of tau 2 tk of tau 3 tm of tau 4, and as usual this will be equal to 0 plus anomalies plus contact terms. And now let me make them very explicit. So the contact terms I have are delta tau 1, 2, p-dimensional delta function. Then I have this L2 function that I defined before, or vector field, as an index I, a lambda, sorry, this is lambda ITI, and I'm missing some indices here. Lambda EJ EK. Sorry, no, I shouldn't have this. No, of course. Well, I have here the TI at 1 and at tau 1 and Tm at tau 4. So this is an extra delta function that I have, but actually we had here 2 delta functions because I eliminated 2 operators. So this comes when I had delta of tau 1, 2, delta of tau 1, 3. So all the 3 operators, Ti, Tj, Tk, got replaced with this Ti here. So this is why I told you that this L2 captures the contact term where T appears as a contact term in 3T OPs. It appears here plus permutations, plus other, so delta 1, 3, and so on. Plus, in principle, higher order deltas. So, if you want to go through the trouble of identifying your metric explicitly, the metric on the conformal manifold, then the contact term that appears there gives you the Christoffel symbol. If you calculated the 4-point function, including contact terms, then you get L2, and that tells you the next order what your killing vector is, and from that you can reconstruct your metric at the next order. And you can calculate from this the curvature invariant.
This four-point function computation is just based on conformal symmetry.
No, what do you mean?
I say it's general for any CFT or just for symmetry theory for n equals 3.
I wrote a 4-point function. I didn't compute it.
First line to second.
I integrated over a 4-point function.
This go to the second line. This inequality is just based on conformal any CFT or for specific CFT.
This is true for any CFT because I didn't say what CFT this is. This is a 4-point function, any defect CFT where the defect breaks part of the part of the global symmetry. You're going to have such a 4-point function. In that case, the integral, when these points are, sorry, this is delta 2, 3. I integrate over tau. I integrate over tau 1. So that makes so any of them could have, it will be 0 unless some points, if these 2 points coincide, there could be an extra term here. When this in the integral hits these 2 points, you're going to get this kind of term, and so on. And this is true in any CFT, so any defect CFT. So if you have a calculation and you do this integral and you read what the contact term is, you know what the vector field is at quadratic order. But that is a bit of a ugly and pointless calculation to do. What you really want to calculate is this L2 lambda WW minus L2 double lambda W, which is a curvature covariant quantity, the Riemann tensor. Here, these, just to avoid confusion, this is WI, EI. So here I wrote it for basis vectors, but in general, the previous expression was for general functions. And you can choose now any scheme to do this calculation. And in order to pick up this term, in here, what you can do is a double integral, dp tau 1, dp tau 2. And I take an arbitrary function of tau 1 and my 4-point function in any scheme that I want that will regularize it. And this will give me, I'm not keeping track of the indices because I'm going to make a mistake, that gives me L2. And now I can change this integral to an integral over cross ratios. and this will become integral dz or d2z, depending on the dimension, over the cross ratio, and a log of z and t of 0, t of z, t of 1, t infinity. So essentially L2 minus L2 will be equal to twice this. And this will be equal to the Riemann tensor, which is going to be delta ij delta kl minus delta ik I L delta j. Okay, am I doing it right? Yes. And what? M. Yeah. To avoid confusions with M. And there's going to be a 1 over there's going to be a CT upstairs. So this is an integral identity of the 4-point function of the tilts that gives you a very fixed quantity with a prefactor. And if you look at this at disconnected level, each of those will be CT squared. So this would be CT, this would be CT. You actually need to subtract here the disconnected part. But the connected part ends up being proportional to the 2-point function, which is really the 2-point function that appeared here. So there's some overall thing, and then the 2-point function. So you get a quantity here that is a 2-point function out of the 4-point function, and the tensor structure is completely determined. And this is the quantity that also the other papers, this is the identity that also the other papers found. And it's another relation satisfied by, in any CFT, by these quantities. It looks a bit weird that I tell you that this is related to L2, which is a double contact term, and I get it from calculating things at separated points, but that's what this funny measure does. Essentially, these 3 points were at the same 1 point, but I was able to split them and move them to finite distances. So this identity will be satisfied by the ones that were good here and will not be satisfied by the bad ones here. It's also satisfied in the ON model if you do the calculation correctly. Then you need to be a bit careful about all kinds of things.
So this, in the end, you get the tensor structure, Riemann tensor, and then this result for any defect CFT. And also, you will see the right-hand side structure is due to the contact term. That's right. If you do not put the contact term, you will not see.
No. So the right-hand side, I cheated a bit. This is correct. This is the Riemann tensor only for a symmetric space. So in some other cases, you're going to get something different. And I don't, in this case, I have a choice whether to put a contact term or not. Generally, if I had here a choice to not put a contact term, the answer would be 0. But I don't have that choice. So this is exactly the point of my talk, that some contact terms are your choice, are a choice of coordinates. Some contact terms are a choice of God, and you are not allowed to mess with them. And the whole point of this analysis is L2 is like the contact terms. L2 has a lot of freedom in it, But part of it is determined. And the part that is determined is what you want, because that gives you a non-trivial identity that these correlations functions satisfy. Now, let me give you one last identity. So this only involves L2, so only 3 tilts coming together. And I told you that actually one of the tilts, it doesn't matter if it's a tilt, I get the same kind of identity if I put here O and O. There's going to be some J and O, and J is some charge of this operator O. And I'm probably messing up something here. But that's essentially correct. And if you really want to know what happens with 4 tilts, you need to take all of them on top of each other. And for that, you need a different measure. And after quite a lot of work, what you find is for p equals 2, the integral d2z z minus z bar squared in a measure which is a function known as d1, or to other people it's known as the massless box integral, or some function with logarithms, or so on, or Davidichev somebody function. Don't remember the other one, sorry. Times the 4-point function. This is an integer divided by, I think, 16 pi cubed. So that there is another global anomaly that can appear in 2-dimensional surfaces. And we calculated it in the 2,0 theory, and this z is really the n of the rank of the 0 theory. More familiar probably would be if I take here dd, dd, and actually the same measure. And in p equals 2, surface defects can have 3 types of anomalies. And one of them will be proportional. So depending how you call it, d1 will be proportional to the 2-point function of the displacements. That's the anomaly I somehow mentioned there already. And this is going to be equal to the A anomaly plus some number. So this is the A anomaly that exists in these 2-dimensional defect CFTs. That is the thing that is monotonic under a defect RG flow. And so it's a quantity you want to calculate. And people have calculated it in several different ways. But this is a new way to extract it from correlation functions of displacements. And this we evaluated explicitly in the case of the 2,0 theory and the case of surface operators in the ON model. And of course, it gives us the right answer because calculations are correct and our derivation is correct. And more surprisingly, the other people's calculations are also correct. No, not surprisingly. So we found some mistakes in the literature when we applied these. The examples that I gave before were not mistakes. They just didn't know this identity, so there's extra information. Some other case, we found some small mistakes. And surprisingly, nothing too crucial. So to conclude, I can make sense of the identity that I wrote before, relating a smooth profile for the coupling, for the shape of the defect, or for the coupling to the global symmetry in terms of correlation functions of these local operators that indicate infinitesimal transformation. There is an ambiguity. The ambiguity is obvious, but there are also quantities that are unambiguous, and we find a lot of these relations. The formalism is quite complicated. A lot of what we find reproduces known quantities like the two-point function, so we again derive this identity that is quite familiar, but other identities are new for existing quantities, and in many cases, if you have when people calculate some quantities to a given order, these relations would allow you to find something at the next order in perturbation theory. So that's all I wanted to say. Thank you. Would you expect there to be a lower bound on A? Well, can't you float a trivial defect? Or there are trivial defects, right?
Examples where A is negative.
Okay.
If it's counting degrees of freedom, just intuitively, people think it should have.
Well, I haven't looked at that question. I don't know if it's useful for that. Well, but maybe then this combination. Yeah.
To my knowledge, that's the first time somebody's related A to like a local correlator of
Yeah.
displacement.
Even this your correlator are related to anomalies.
Even P, yes.
Yeah, even P.
Yeah.
Um,
Well, but also.
in
So in the line defect, the three-point function of the tilts is also related to an anomaly, but not a conformal anomaly. It's a global anomaly of this SU2 group, which quantizes the level of a WZW model, or quantizes the flux in string theory, if you didn't know that the flux was quantized.
I don't see anything special about why P is equal to 2 in that last expression you wrote.
Why what?
I mean, you put P equal to 2 in this derivative expression, but in principle, that doesn't change if you put 1 or 3.
So I had to derive this measure for 1 and 3. I don't. So there. Again, the three-point function of tilts. So generally, I would expect there to be anomalies. For that there would be some kind of context where there would be anomalies, at least global anomalies. Like here, so this happens for 2 dimensions. Yeah, in 1 dimension, there is no anomaly here. So we classified, I told you this, yeah, so there is some cohomological argument in which dimension these global tilt anomalies appear, and they appear in the 3-point function for line defects. They appear in the 4-point function for surface defect. They appear in the 5-point functions for 3-dimensional defects, but we haven't completely analyzed that case. So I don't know. In that case, maybe there are other anomalies. This probably something like this also happens for p equals 4. We didn't go through that exercise. For the displacement, do you remember if we looked what the integral in 1 dimension would give if it's automatically 0? Yeah. Yeah, I don't quite remember what are the possible anomalies for displacements, and if there is anything that comes. No, but that's in 2D, not in 1D. But this A2D is in 2D. Yeah, so we actually haven't finished the full classification of anomalies, and we're not going to go above p equals 3. It gets really hairy. Above p equals 2 to make general statements, but in some cases there are anomalies, in some cases there aren't. Generally there are. Of one kind or another. There is something we suspect is a gravitational anomaly, but we haven't fully figured it out. So it's a bit complicated, but what you do is you look at the quantity like this. So this integral, so you write an integral somehow of this form. If you have a higher point function, you need here more. This may depend on more fields. That will pick up this term. Okay, there's a delta function here that's not too hard to find. An integral like that will pick this up. And now you know which combinations of L2s you want, for example, that is scheme independent. So you do that symmetrization, and then you try to write it in a way that is conformally invariant. You deal with the regularization. So you work in a particular scheme, you deal with the regularization, then you extract the quantity that is conformally invariant, and then you can rescale your coordinates back to a form like that, and this measure pops out. See, when are you going to do a calculation like that on Friday or no? No, you're not doing complicated measures. Yeah, it's about a page of calculations. It's not 2 pages. It's not immediate. This is a box, a regular box. Or if you know ADS-CFT, this is the simplest 4-point Witten diagram. It's log squared plus dilog. Sometimes written as capital phi. I don't know what the next one is. I haven't. It's really a mystery why we got this D1111. The most obvious most famous transcendentality 1 function is log z, unless you consider pi. Okay, this is the most famous transcendentality 2 function. So I guess the next one would be the most famous transcendentality 3 function. It's complete mystery to me why why we got this function. There must be a very deep reason for this, which is evading us.